Hi, we are GenePy. My name is Ezra. My partner is David. And so in this video, we'll go over a brief introduction to GenePy and then go over some demonstrations on using GenePy and some examples. So the goals and motivations behind this project. With this project, we are essentially porting the functionality of Eugene, and more specifically miniEugene, which is a light version of the greater Eugene ecosystem, into a Python tool called GenePy. And so the motivation behind this was to essentially make Eugene functionality more accessible to users. Those users being either researchers that are interested in exploring Eugene and wanting to get familiar with some of the Eugene tools available, and also for developers that are interested in integrating Eugene and other specification type functionalities into their larger automated workflows. Through this project, we hopefully are able to demonstrate that. And so now I'll go into kind of the two main components of GenePy and high level how it works. So GenePy is made up of two main components. The first is a class, and so this class contains a variety of different methods that enables users to use the Eugene functionality in a Python environment. The second component of GenePy is the GUI, and the GUI runs on top of the class and enables users that don't have a strong programming background to still be able to explore the GenePy project. And then with both modes of operation, users will still be able to get either a sequence or a list of sequences that fit their user-defined rules.
All right, here we're going to demonstrate two test cases using the graphical user interface. Test one will add a bunch of rules that will verify the end sequence that's generated by the system. And in test two, we are going to add another rule to the test one that conflicts one of the rules, and we'll observe the result of adding a conflicting rule onto a system. So this is the main window of the GUI. We have two text boxes where you can input the desired length of a sequence, and another one for inputting the desired number of solutions. And the launch console window button launches the console window, and this is where the system will display all the rules the user put in, along with the generated output sequence after the user presses the run solver button. And here we see each one. Here we see a add rule button, one for each rule in miniEugene and Eugene. And we have counting rules, pairing rules, position rules, orientation rules, and interaction rules. So to move on, we're going to add some rules and start testing with it. So the sequence length I desire for this demo is 10, let's say, and the number of solution I want is, let's say, 5. And rule 1 would be these sequences include part P1. And the second rule will be these sequences have 2 of part 2, P2, exactly. And these sequences will have P3 part, more than one of it on each of the sequences. And we have P2. Some of the P2 comes before P3. And all of these sequences will end with P3. And lastly, we're going to say part P1 induces part P3. And here you can see all the rules that I put in on the console window. So these are the rules that's inside the system. And since I filled out the text boxes at the beginning, we are ready to run the solver and see what's the output. And here we see 5 sequences as we input onto the text box here. And each one of them are 10 parts long exactly. So we can see that these two constraints we set up at the beginning of the test holds up together within the system. And let's see if the rules hold up together. So all the sequences should contain P1. We see numerous P1s here. So that's fine. Each of the sequences should contain exactly 2 P2s. Here we see 2 P2s at the beginning of each of the sequences. We don't see any more at the later half of the sequences. So that's good. There should be more than one P3. There doesn't seem to be a problem there. Some P2 should be before P3. Well, P2s are the beginnings of each of the sequences, so that's met properly. And all the sequence should end with P3. That seems to be the case. And P1 induces P3, meaning some of the P1 should be behind P3. Here we see here, there, P1 pointing to P3, here and there. So looking at the output sequence, it seems that all the rules that we put into the system holds up together. And that's a good thing for test 1. For test 2, we're going to add a rule that goes directly against one of the rules that we input before. So for example, let's say, since all the sequences are required to end with P3, I'm going to add a rule that says these sequences should also end with P2. And this rule goes directly against this rule, which means that the expected behavior of the solver should be returning some sort of an error. And let's see if that is the case. Happens offsite, so let's see if I can run it again. Okay, yes. So it's not displayed on the console yet. The functionality is still work in progress, but the constraint solving algorithm we put it onto our system returns an error, meaning that it was not able to resolve the constraints we put into the system, which is a good thing since we designed test 2 to be a failure.
And so David went over the GUI, and then I'll kind of start going over a demo example or a demo test or example script of how you would use GenePy in a Python script. And so first you would import the GenePy class, and then you would then create an instance of that class. And so when initializing, you need to pass in an integer or number, and this should reflect the size of the sequence that you're looking for. So how many parts in the sequence exist. And so this must be predefined before doing anything else. After that, we then kind of follow the same formatting style that miniEugene has in terms of how rules are declared and kind of stylistically and to make sure that they're both the same. And so first here we have the counting rules. And so with any of these rules, users should be able to easily declare them by using the dot operator and then entering the rule that they want to declare. And then the arguments for each of these methods should be the parts that you want the rules to apply. So for now, these parts are just abstract strings. And so for an example here, we have GP contains P1, GP exactly P2 2, and GP more than P3 1. And so for the rules that have 2 arguments, so exactly and more than, The formatting that this follows, so the first argument will be the part, and then the second argument will be the number relevant to the rule at hand. And so for the positioning rules, the same ideas apply here, where we are trying to essentially mimic the same nomenclature and style that miniEugene has. And so with any rules that might have more than one argument, like with alpha and beta, so for example, in the sum before, the first argument will always be the first argument again in the method, and then the second argument will be what you might often see as beta and miniEugene documentation. And so for example, you would read this as P2 sum before P3. And so following positioning rules, we've also show some interaction rules. And so here we're showing the use of induces. And then so you would read this in miniEugene as P1 induces P3. And so after declaring all your rules, you can then access these rules later on in your script by accessing the class variable rules. And so because this is a nested dictionary, you can then access the rules you're looking for by passing in the key value of the rule of interest. And so for here, for example, we're going to print out all of the parts that have been declared under the induces rule. And so lastly, we can then generate, or sorry, not lastly, but in terms of declaring rules, we then are able to generate sequences. And so with the .generate method, and so here, this method can take either no arguments or number arguments. And so with no arguments, it defaults to giving you all potential sequences. And by passing the number, you are restricting the amount of sequences that you see. And so lastly, we can then write the rules and solutions generated by our script to JSON files so that they can be easily accessed later on, or if you want to integrate GenePy with other software tools, which should make it simple to do. And so after writing the script out, we can then run it and observe our outputs in the terminal. And so, as you can see here, the first output is the printing of the induces rules. And so the key value here, the key value pairs directly reflect the declared induces rules. And so that's good. And then lastly, here we have a list of all the sequences that were generated. And so GenePy, when giving you more than one sequence, will format that in a list of dictionaries. And so that's what we see here, which is good. And so thank you for listening. That kind of wraps up our demo video. For more information and for further documentation into the project, please check out our GitHub. Thank you.